Yeah, hi everyone. Thanks for coming. I hope you have enjoyed the lunch. Today I want to tell you a little bit about why and how we are currently redesigning Flink's distributed architecture. To quickly introduce myself, I'm Till and working as a software engineer at Data Artisans. And these days I mostly spend my time working on exactly this. So, to begin with, I want to share a little wisdom with you, and that is that one does not simply change one's cluster environment. Everyone of you who had the task to set up a new cluster environment in your company knows that this is often not an easy task, and one would like to avoid it. So this also means that if you are supposed to run like an application like Flink, for example, on your cluster, which does not support your company's cluster environment, then you usually end up not using this framework rather than installing or setting up a new cluster environment to make it work. This, of course, entails for frameworks like Flink that it better should support as many different deployment scenarios as possible, so that it is applicable to as many users as possible. To name a few of these cluster managers, there's, for example, Yarn, which I think most Flink users use to deploy Flink. But recently, we've also seen on the mailing list an increased interest in Apache Mesos, and people also asked for running Flink in a containerized environment using Docker Swarm or Kubernetes. And we should not forget Flink's first deployment mode, the Standalone, where you basically deploy Flink on a bare metal cluster. All these different deployment scenarios follow slightly different paradigms, and that's exactly the challenge for Flink to support the variety of these different paradigms. Apart from the different deployment scenarios, we've also seen that Flink is used differently by many users. Some users, for example, run long-running streaming jobs on a Flink cluster, such that they have like a dedicated cluster for it. So there's only a single job on a cluster. Like an application or like a use case for that would be doing like some fraud detection on a stream of credit card transactions, for example. Other users, again, they offer Flink as a service internally, and thus might run many short-lived batch jobs coming from their data science department, for example. And in that case, you would like to avoid the overhead of starting for each job like a cluster, and rather you would like to have a long-running cluster to which you can submit the jobs. Another dimension to distinguish the usage patterns, Flink usage patterns, is whether jobs are supposed to run in strict isolation versus sharing resources of a cluster. The former case is interesting for all the people who want to make sure that jobs don't interfere with each other, and for those who want to assign, want to run their jobs with a certain user credentials, for example. If you run multiple short-lived jobs, then in order to increase like the resource utilization, then you might be interested more in having a cluster where the task manager runs basically multiple concurrent jobs. So that's also important for Flink. So in order to cover these different usage patterns, Flink has the notion of the execution has the notion of a job and a session mode. The job mode is basically that you have a dedicated cluster per job, and as soon as the job is finished, the cluster will also be shut down. And in order to cover the resource sharing case, there's the session mode, which basically allows you to submit multiple jobs to a cluster, which can also share, like can be executed, like that tasks of multiple jobs can be executed on the same task manager. So we try to keep these two execution modes in mind because that's important that we realize we offer these execution modes with the new Flink design as well. And we'll see in a minute how we address them. Before we dive into the new architecture, let's take a look at the current state of Flink. Historically seen, the Flink standalone mode was the first execution mode, and it worked the following way: that you started a standalone Flink cluster, which consists of a job manager or multiple job managers in case of high availability, and a fixed set of task managers, which you start on the other machines of your cluster. The task managers retrieve the address of the job manager via the configuration, or in case of high availability from Zookeeper, and connect to the job manager. Once they're registered, they also tell the job manager how many slots they have available. So now if you want to run a job on your Flink cluster, you use the Flink client to submit a job to the job manager, which will translate the job into an execution graph and deploy the tasks onto the different task managers, to basically run the job. In this mode, you're also able to submit not only one job, but multiple jobs to the job manager, which can run concurrently. If you should submit too many jobs, or your jobs require too many slots, which the job manager does not have at the time of submission, then the job will fail with a no resource available exception. So this case can also occur if you try to too eagerly submit a job to a cluster which has just been started, because the registration of the task managers at the job manager usually takes some time. The Flink-on-YARN job mode looks the following way. Already from a high-level perspective, you can see that it's a bit more complicated because there are many more errors and steps involved here. So how this currently implemented is that if you want to submit a job in the job mode on YARN, the client connects the YARN resource manager. It submits a YARN application containing the Flink cluster. So the YARN resource manager will then allocate a container and spawn an application master. This application master basically runs the job manager and allocates a fixed set of YARN container to run task managers in it. Once the application master has been started, the client will start constantly polling against this cluster, polling the cluster status in order to know how many task managers have registered. Once all task managers have registered at the job manager, the client will notice that by seeing the respective status, and only then it will submit the job to the cluster. That is because otherwise we could submit a job too early, and it would not execute because of the no resource available exception. And once the job is submitted, the job manager will deploy the task onto the task managers. So what you can see here is that we have this kind of two-phase job submission step, which is not only a bad design, but also brittle. And with the new design, we will see how we can solve this problem much more elegantly. All right, that should be enough for a quick recap of Flink's current state. Now let's try to summarize some of the problems we have with the current design. So first of all, we have no clear separation of concerns on the side of the job manager. The job manager is not only responsible for a single job, but it is actually responsible for running multiple jobs, which internally makes the logic a bit more complicated. Furthermore, it is, the job manager is responsible for managing also task manager connections, even though it should only be concerned with task slots into which it can deploy tasks. Then we have the problem that there's no dynamic resource allocation possible at the moment. So if you have a job which where the workload suddenly increases, the Flink cannot react to it by starting new task managers, for example. What you haven't seen, what I can tell you is that at the moment, all of the task managers are started with the same set of resources, and these resources are equally split among the task slots. This has the consequence that all task slots have the same set of resources. So usually in a job, you will have operators which require a bit more resources and others a bit fewer resources. For example, like a non-CPU intensive mapper and then a memory and CPU intensive reducer. That's not possible to support at the moment, but in the wake of the redesign, we've introduced a feature to do that. And last but not least, due to this two-phase submission step of the job, Flink does not play well along with containerized execution, because like these container frameworks usually assume that your containerized application is self-contained and does not require an additional external service like a client submitting a job to it. But that we can also solve with a new design. All right. Now, since you've seen the problem, let's take a look at how we try to solve them. So the whole redesign is done under the umbrella of the Flink Improvement Proposal 6, short Flip 6, which basically has the idea to introduce generic building blocks which can be composed together, like for every deployment scenario a little bit differently, such that we can fulfill their requirements. This effort is mainly driven by Alibaba and data artisans. And if you want to take a look at the official design documents, you can follow the link at the bottom of the page, the slide. Wrong direction, sorry. So what are these generic building blocks? So we've identified four building blocks. These are the resource manager, the dispatcher, the job manager, and the task manager. The resource manager is a cluster manager specific component which may live across jobs. Its task is to manage the containers and the task manager which run in them. And it is supposed to acquire and release new resources, new containers in case of like that the workload increases or decreases. Then we have the dispatcher, which also lives across jobs, and is basically the touch point for the client when it submits new jobs. The task of the dispatcher is basically to receive the job and spawn a new job manager running exactly this job. And it can also spawn a resource manager in case that there's none yet. The job manager is changed in the way that it no longer supports multiple job execution, but is only responsible for a single job. That's makes things much easier. And it only thinks in terms of task slots, so it does not really know about the task managers anymore. And its actual job is to deploy and monitor the tasks of the job it is supposed to execute. And the tasks are then executed on the task manager, which can also execute tasks from different jobs actually, or different job managers. So that it's not exclusively assigned to a single job manager. So since all theory is gray, let's take a look at how we can combine these building blocks to build a running Flink cluster. We assume that we have a dispatcher and a resource manager running, and now we want to submit a job. So what we do is the client will, we will start a client with a job, and the client will submit this job to the dispatcher. The dispatcher will then start a job manager, initialized with this job. The job manager will connect to a resource manager and request slots for the job execution. In case that the resource manager cannot fulfill these slot requests because there are not enough slots available, it will start a new task manager, which registers at the resource manager and declares how many slots he has available. With these slots, we can fulfill then the slot requests, offer the slots to the job manager, and the job manager can finally deploy its tasks to the task manager. And that's basically how the different building blocks interact with each other. All right. Having defined these building blocks, we can now take a look how we built the Yarn job mode, the Flink-on-YARN job mode. So how we do it is the following way. We have our Yarn cluster, and again, we need our Yarn cluster client. And this client submits, again, a Yarn application, but this time it not only includes the Flink cluster, but also the job graph, so the job, and all user code jars. With that, the Yarn resource manager will spawn an application master, which contains a Flink-YARN resource manager and a job manager, which is initialized with the submitted job. And now what happens is basically what I've described on the slide before. The job manager will connect to the resource manager, request slots. If there are not enough slots available, the resource manager will allocate new containers from Yarn and start task managers in them, which then register at the resource manager. And once the job manager has its slots, it can deploy the tasks onto the different task managers. And here what we also see is that in this case the job manager and resource manager run in the same process, but it's also possible that the job manager is executed in a dedicated container. That's up to the how you compose the blocks. So the differences to the old Yarn mode are the following: that we know all the jars of the user code up front. So we can start all components with these jars in the class path, and consequently we can avoid having to load user code classes, which was in the past always a hassle and led to many bugs basically. Then finally we added like dynamic resource allocation, so that now the Flink-YARN cluster can allocate and release containers. And last point, we got rid of the two-phase job submission step. So the whole process of submitting a job became much more simple because we no longer have to poll and after and wait until all task managers have registered at the job manager, resource manager. All right, how does it look like for Mesos? It looks quite similar, with the only difference that we connect to the Flink-Mesos dispatcher. A side note: in the Mesos world, the Yarn applications are called like Mesos frameworks. And every parent is supposed to watch its children in order to restart them in case of failure. And the root element of your framework can be made highly available by using the Marathon framework. And our root would be the dispatcher. So how would deployment look like? Well, we could send an HTTP post request to the Flink-Mesos dispatcher containing the job and the jars you want to run. Then the dispatcher would allocate a Mesos container and start a start the Flink master process in this container. And it would also start supervising this container. So in case it fails, it would restart it. And from there on, well, we see that we also have a resource manager, this time a Mesos resource manager, because it has to communicate with the Mesos master, and the same job manager and task manager components. And from there on, it's basically the same as in the YARN case. The job manager requests slots, the resource manager tries to fulfill them, and then the job manager wants the task in the assigned slots. All right. So much for the YARN and Mesos case. What about the containerized execution? So one way to run a Flink job in a containerized setting is that we have our container framework, which starts a master and worker container. The master container contains the Flink master process, running a Flink container resource manager, and a program runner. You can think of this program runner as a kind of dispatcher, which has a predefined or a single predefined job. And once this program runner is started, it will spawn a job manager with exactly this job to execute. And then we have our worker containers, which simply contain the task manager. And these task manager will register at the resource manager, and then the job manager can basically execute the job on it. So what we basically have is we have two types of containers. The one containing the dedicated resource and job manager, and then another container type running the task managers. This can actually be a kind of blueprint for all external systems which control resources and start new task managers, for example. We could even go one step further, that we say we don't have like two container types, but a single one, which is like a general purpose container. And that in order to start a cluster, we start n containers of this type. And then we use something like leader election to decide which of the containers is going to become the job manager, and which is going to become, or which containers are going to become the task managers. And that way, we basically have some kind of similar deployment capabilities as we also have with, or as one has with Kafka Streams, for example, where if you need some more resources, you simply spawn up a new container. It will decide what it is, automatically decide what it has to do, and then connect to the job manager and help processing the job. And what you also could do is enable auto-scaling groups, which are controlled by the external system. We could do that by basically giving all the available slots, which are registered at the resource manager, automatically to the job manager. And whenever the job manager receives new slots or loses slots, it will rescale the job to the current maximum number of available slots, which is also quite easy. All right. So much for the job mode execution. Now let's take a look at how we can implement the second mode, the session mode, where we run multiple jobs on a single cluster. For that, we first take a look at the standalone case. Here we have basically a Flink master process running on a machine. And this master process contains the standalone resource manager and a dispatcher. And additionally, we have to start some task managers on some other machines. And these task managers will then, first step, what they do is they register again at the resource manager. So this is the recurring pattern, and wait there for a moment. In order to submit a job now, the client will connect to the dispatcher, which spawns for the submitted job a new job manager. And from there on, it is again the same procedure as in the Yarn and Mesos case, requesting slots, obtaining the slots, and then executing the tasks. And in the standalone case, in the session, or since we want to be able to run multiple jobs on our cluster, the dispatcher can receive multiple jobs, and for each job it will spawn a new job manager. And in order to achieve high availability, we could also start some standby master processes, which where we use, again, leader election to decide which of the processes is responsible for the job execution. If you now take a look at the yarn session, it looks actually almost identical. The only difference is that you first have to start a yarn session by using the client, submitting a yarn application containing this time only the cluster to the yarn resource manager, which then spawns the application master. And here again, in the session mode, the application master only contains the resource manager and the dispatcher. And only after the client has submitted a job to the cluster, basically sending the dispatcher the job managers are started. In this implementation, the job manager is started within the application master process, but it could also be that we allocate dedicated containers for them. And then the job, as in the previous figures, requesting slots, starting task managers if needed, and then deploying the task into the slots. Okay, so what we've seen in order to implement the multi-job sessions is that we have a dispatcher instead of an initialized job manager. And this dispatcher basically has the task to spawn for every received job a dedicated job manager. Additionally, we see, or what we have in the session mode, that all the jobs which are executed basically run under the same session credentials, which are those, which are the credentials which we have used to basically start it. A thing which works a bit differently in the session mode is that here we allow the resource manager to hold on to some of the task managers for some time after all of their slots have been released. This has the advantage that if we have like successive jobs, we can basically reuse them and don't have to allocate new containers from Yarn, which might take some time. So it basically gives us better response times. All right, so much for the multi-job sessions. So in the wake of rewriting the distributed architecture, we also added some other functionality. One I've mentioned, one which is related to one of the problems I mentioned before, are the resource profiles, which allow you to specify for each operator how much resources it needs. And this resource profile will be part of the slot request, which is sent to the resource manager. And the resource manager now will make sure that the job manager will get a slot which has at least as many resources as requested in the resource profile. And that way we can basically control for different operators in which, how many resources the slots have in which the operator is executed. And we added a new RPC abstraction, which, before you have to know, we used plain akka actors. And this new RPC abstraction is a bit more similar to Akka's typed actors, where you basically have a properly defined interface for your remote components. This has the benefit. Well, the problem before was that, if you don't know the code of your actor and it's not well documented, then someone programming against it, does not really know what the actor supports in terms of functionality. If you have like a properly defined interface, then it's much easier. It has, in that way we hope that it will ease Flink's future development. And another nice thing is that we are no longer locked in on Akka, because the actual RPC abstraction or the actual RPC implementation can be easily swapped out using something like Netty-based implementation or anything else which can send data over the network. And with that, I'd like to come to the conclusion of this talk. So what you've hopefully seen today is or what I've tried to motivate is that there are many different cluster environments in which people would like to run Flink. And in order to be, well, as wide applicable as possible, Flink should support as many, if not all, of these scenarios. Additionally, there's due to Flink's broad usage, we have to support what we call a job and a session mode. Namely running a job in a dedicated cluster versus running multiple jobs in one cluster. With Flip 6 and the introduction of these generic building blocks, which can be flexibly composed in a flexible manner, we are now in the position to support many of these deployment scenarios as well as execution modes. And so the actual goal of the redesign was that we improve Flink's position for the future and to be also ready for new upcoming deployment modes. I think that's what we have achieved or are achieving currently. Yes, that's all I wanted to tell you. Thanks a lot for your attention. If you want to stay updated on Flink's development, I can recommend you following Apache Flink or the Data Artisans Twitter account. Or if you want to learn more about other things like the APIs and so on, I can recommend reading the Stream Processing and Apache Flink book. I think currently there are 3 chapters online, and more are coming. And if you think Flink is a nice project and I want to work on it while also getting paid for it, I can recommend you applying at Data Artisans, because we are currently hiring and looking for helping hands. Thanks a lot for your attention.
So you mentioned that rescaling the job. Does that include the stop job and the start job again?
Well, at the moment, yes, it does.
You said that you could pre-specify like a resource profile, and then for different operators with different resource demands, I think it was the job manager then would basically allocate more resources to the ones that you specified. Could there be like an auto-tuning where it actually detects whether like certain operators take longer or use up more resources, and then automatically basically react to that? Because I don't know sometime in advance probably exactly what my resource demands are, right?
Well, that's not how, at least at the moment, it is intended to be used. It's admittedly, it's an advanced feature for people who know that like this one operator is more compute intensive than this one, and they can roughly estimate first of all, how many resources they want to provide in total, and then how they should be distributed over all operators. But I think that would be an interesting thought to try to automatically come up with to infer how many resources an operator needs. But this won't be solved with the first iteration of this. Yeah.
In the multi-job sessions, can the resource manager hold on to the job manager for reuse?
No, because the job manager is dedicated to a single job, but the resource manager can hold on to the task managers to reuse them basically, so that you don't have to allocate every time new containers from Yarn, which depending on how heavily your Yarn cluster is used, can take some time.
So with the resource profiles, right? Is it like the mode will be kind of heterogeneous at my infrastructure level, which means some task managers can be a little bigger nodes and some task managers can be smaller ones? Or is it like that across the graph, you take the max profile and ask for resources, that many task manager resources?
The way we currently think to implement it in the first iteration is that is mainly used for the Yarn use case, where you basically deploy every operator in a single task manager. So you will basically have then task manager with differently sized slots. But in the future, one thing to improve is, for example, accumulating these resource profiles to create like a larger task manager with accumulated resources, and then having differently sized slots on this task manager. Yeah.
When is this work expected to land?
Some of the work is already in the master. For example, Alibaba has a fork using some of the code already. The goal was actually to use the Flip6 code for the Yarn mode in Flink-on-3, but most likely it looks at the moment that it will come with 1.4. So not at the end of May, but at the end of August then, I think, or September. Yes.
Do you recommend any one of those for a new project?
1 second, please.
You supported all of them, but is there one that you would recommend if you're starting a project now? I mean, the last one seems like the simplest, but Yarn, you said, is the most widely used.
I would say it depends on what kind of infrastructure you have available. If that's one infrastructure which is supported by Flink, I would use that one. At the moment, if you want to use Flink right now, I would recommend you to use Yarn, which is still the best supported resource manager with the most functionality. But there are also people using it with Mesos. Mesos code is out there, so it's not. The only thing is that it's not yet fully, functional-wise, on the same level as the Yarn thing, Yarn code. But in the future, once this Flip6 is ready, all the different Mesos Yarn and the Dockerized or the container execution should be equally well supported. Yes.
Any other questions?
Okay.
Okay. Thank you.
Thanks.